All right, so when we think about vectors, we usually picture them doing simple stuff, right? Like getting longer, shorter, maybe flipping around. But what about when they spin? That's what we're digging into today. We're going to uncover this beautiful mathematical code that describes rotation, and you'll see it secretly running the show in everything from electrical circuits to the orbits of planets. Okay, let's break this down. On the one hand, you have transformations that just stretch things. A vector gets hit by a matrix and boom, it's just a longer or shorter version of itself, still pointing along the exact same line. That's your classic eigenvector behavior. But then you have the stuff on the right. This is where it gets really cool. The vector isn't just stretching, it's spinning, spiraling around the origin, completely leaving its original path behind. And this is a real puzzle, right? I mean, the whole definition of an eigenvector is that it's this special direction that a matrix doesn't mess with. It only stretches it. But when something is rotating, every single vector changes its direction. So if there's no fixed eigendirection, how on earth are we supposed to describe this spin using eigenvalues? It feels like we can't. So to get to the bottom of this, we're going to zoom in on one specific matrix that's famous for making things spin. Let's go hunt for its special vectors and see what they tell us. Okay, here it is. Our matrix of interest. It looks super simple, right? Just ones and a minus one. But don't let that fool you. This thing packs a serious punch. Anytime you multiply a vector by it, it gets both rotated and stretched. This little guy holds the key to our whole mystery. So first step, let's find its eigenvalues. All right, we're just going to follow the standard playbook here for finding eigenvalues. We set up the characteristic equation, that's determinant of a minus lambda I equals 0. We crunch the numbers, and what pops out is this characteristic polynomial. Lambda squared minus 2 lambda plus 2 equals 0. Simple enough? The solutions to this equation, our lambdas, are the eigenvalues we're after. But here's where it gets weird. If you plug that equation into the quadratic formula, you run into a big problem. You end up trying to take the square root of a negative number. And, on the good old-fashioned number line, you just can't do that. It means this equation has no real solutions. So what does that mean? Did we hit a dead end? Does our matrix just not have any eigenvalues? Well, the answer isn't that there are no eigenvalues. The answer is we've been looking in the wrong place. To find the solution, we have to expand our toolkit. We need to step off the one-dimensional number line and into a whole new dimension of numbers. And that brings us to complex numbers. Think of them as living on a two-dimensional plane instead of just a line. And voila, the solutions are 1 plus I and 1 minus I. That little I, of course, is the imaginary unit, the square root of -1. These are the eigenvalues of our spinning matrix. They were there all along. And this isn't just some lucky fluke for this one matrix. It's actually a fundamental rule. The fundamental theorem of algebra basically guarantees us that for any n by n matrix, you're going to find exactly n eigenvalues. You just have to be willing to look for them in the complex plane. So our 2 by 2 matrix having 2 complex eigenvalues, that's exactly what the theorem predicts. Okay, but here's the truly mind-blowing part. These complex numbers, 1 plus I and 1 minus I, they're not just some abstract answer to an equation. They're actually a secret code, a blueprint that tells us exactly how our matrix spins and scales vectors. It turns out our matrix, with 1s on the diagonal and -1 and 1 on the off diagonal, belongs to this special family of matrices called rotation-scaling matrices. And check out the pattern. You've got the same number, A, on the main diagonal, and then B and -B on the other diagonal. Anytime you see a matrix that looks like this, it's a dead giveaway. It's a rotation scalar. And its eigenvalues, they're always going to be A plus or minus B times I. It's a direct one-to-one connection. It's really elegant. So let's crack this code. That complex eigenvalue, A plus BI, it's basically a complete instruction manual. The real part, A, and the imaginary part, B, give you the coordinates of a point. The angle that point makes with the origin, that's your angle of rotation. Bam. And the distance from the origin to that point, its magnitude, which you calculate just like the hypotenuse of a triangle, that's your scaling factor. The spin and the stretch, it's all packed right into that one complex number. Okay, let's bring it back to our matrix. Our eigenvalue was 1 plus I. So A is 1 and B is 1. Let's find the scaling factor. It's the square root of 1 squared plus 1 squared, which is just the square root of 2. And the rotation? Well, the point 1, is sitting up there at a perfect 45-degree angle. So there it is. The eigenvalue just told us that our matrix rotates every vector by 45 degrees and stretches it by a factor of √2. The mystery is solved. But what happens if we keep applying this matrix over and over and over again? Well, that scaling factor we just found, the magnitude of the eigenvalue, that's the key. It tells us the entire story of the system's long-term behavior. Basically, it all comes down to the magnitude. If that magnitude is bigger than 1, vectors are going to spiral outwards, getting bigger and bigger with every step. If the magnitude is exactly 1, they don't grow or shrink. They just spin around in a perfect, stable orbit. And if it's less than 1, you guessed it, they spiral inwards, getting closer and closer to the origin until they collapse. Our example, with its scaling factor of the square root of 2, which is about 1.41, falls right into that first category. Since it's bigger than 1, every time we multiply by our matrix, the vectors get longer. This creates this incredible outward spiral where everything is just flying away from the center, getting bigger as it spins. Now, if our eigenvalue's magnitude had been something small, like, say, 0.5, we'd see the total opposite. Every multiplication would shrink the vector. It would still spin, but it would be spiraling inward, getting sucked into the origin like water down a drain. That describes a stable system, one that eventually just settles down to nothing. So you might be thinking, okay, this is a cool little trick for 2D planes, but what about the real world? Well, this idea isn't just limited to 2 dimensions. It's actually one of the fundamental building blocks for understanding how things rotate in much more complex systems. Take 3D, for instance. A 3x3 matrix has 3 eigenvalues, and it's really common to see one of them be real and the other 2 be a complex pair. What does that look like? Well, the real eigenvalue gives you that simple stretch along one axis. But at the same time, that complex pair is creating a spin in the 2D plane perpendicular to that axis. You put them together and you get this amazing corkscrew motion. Something is stretching out in one direction while spinning around it. It's beautiful. So you see, what started out as a purely abstract math problem, what do we do when we can't find a real solution, ends up describing a fundamental behavior of the universe? It really makes you wonder, right? When you look around, from the orbits of planets to the way electricity oscillates in a circuit, what other spiraling, rotating systems out there are secretly being run by the simple, elegant code hidden inside a complex eigenvalue?